So today I would like to introduce a new test for divergence/convergence, which is called the integral test. And so by the end of today, we should be able to use the integral test to show that a series diverges/converges, identify series to which the integral test can be applied. We want to be able to identify logically invalid uses of the integral test as opposed to valid uses of the test. And finally, we're going to, at the end of the video, change track a little bit and talk not about convergence/divergence, but talk about how to use integrals to get an estimate for the actual value of a series. To determine whether a series converges/diverges is asking ourselves the question, does the series have a value? But that's different from the question, what is the value of the series? In general, it's much harder to determine the actual value of the series than it is to determine whether the series actually has a value in the first place. So we're going to talk a little bit about some ways to use integrals to estimate the value of a series. To set the stage, let's think about all the tests and all the techniques that we have so far, and let's acknowledge the fact that none of those techniques can be applied to any one of the series that's listed on this page. 1 over k, natural log of k divided by k, and 1 over k squared. In each case, the divergence test is locked and cannot be used to make any conclusion because all three of the sequences listed here will approach 0 as k goes to infinity. It's quite hard to find a formula for the nth partial sum of each of these series, and so using the original definition of a convergence, taking the limit of the nth partial sum is going to be extremely difficult as well. And not only that, none of these series are telescoping, none of these series are geometric, so we can't use any one of those approaches. So let's introduce a new test that we can use to determine whether these series converge or diverge. And the idea that we're going to use is the fact that all three of these formulas, 1 over k, natural log k over k, and 1 over k squared, all these formulas represent functions which have an antiderivative. The antiderivative of the function 1 over variable with respect to that variable is equal to the natural log of that variable, plus any constant. If we wanted to integrate natural log of variable divided by x, then you can find this result using the u substitution, where u is equal to natural log. Then du would give us that 1 over x dx, and so we can integrate using u substitution. And finally, the integral of 1 over variable squared, which is the same thing as variable to the minus 2, can be integrated using power rule. So we're going to use the fact that each one of these formulas has an integral, and we're going to use that integral to make some conclusions about convergence/divergence. So that brings us to the statement of today's integral test. The setting is just what we saw on the previous page. We have some sequence, a sub k, and the formula for the terms in the sequence is given by a function which is first of all integrable. It's something that we are capable of integrating. But there are a few additional conditions that need to be satisfied. On some right infinite interval, for all the inputs which are greater than or equal to some starting number, we need to make sure that our function is continuous, decreasing, and positive. So this is part of the setup, this is part of the hypotheses that need to be satisfied to even begin to use this theorem. Now suppose you're in this setting and you integrate from this starting number up to infinity. Integrate this function which is giving you the terms in your sequence. If this improper integral from starting number to infinity converges, if this integral equals a finite number, then guess what? The series, starting at the starting number, must also converge. So the big takeaway is that if you have a sufficiently well-behaved formula for the terms in your sequence, something that you are able to integrate, then you're in fantastic luck, because then you can go back to Calculus 2, integrate that function, check and see if it converges. If it does, then your series must also be convergent. Not only that, if you calculate that integral, and the result happens to be divergent, you get something that's not a finite number, then the series actually has to diverge in that case as well. In other words, there's always a matching between the behavior of the improper integral and the behavior of the series. So let's go ahead and get some practice applying that theorem to a series like the following. I'm going to investigate the series where I'm summing as k goes from 1 to infinity, k divided by e to the power k squared. And let's give a formal argument. In other words, convince the skeptic. In other words, convince me. So the first thing that I'm going to do is I'm going to pop out to a graphing calculator program, for example, desmos.com, and I'm going to graph the function that gives us the formula for the sequence for our series. Now, looking at this function, from x equals 1, which is right about here, x equals 1, off to infinity, we can confirm by the graph that the function is continuous, there's no holes in the graph. The function is decreasing because it's going down from x equals 1 off to infinity. And we can confirm that the function is also positive because it's always above the x-axis. So from the graph, of the function, whose formula is given by variable divided by e to the variable squared, we can confirm that this function is continuous, positive, and decreasing on the interval where x goes from 1 all the way off to positive infinity. For the entirety of the graph to the right of x equals 1, the function satisfies these three properties, which means that we're in the position where integral test is starting to become unlocked. The first things that we needed to be true are indeed true. So next, let's go ahead and let's investigate the integral of this function from x equals 1, the starting number, to x equals infinity. So let's rewrite this expression a little bit to make it easier to integrate. Instead of dividing by e to the x squared, I'm going to think of this as multiplying by e to the negative x squared, moving that quantity out of the denominator at the price of making the exponent negative. Once I've rewritten the integrand in this fashion, let's use a u substitution. For example, I think that a nice one here might be u equals negative x squared, because then the du is equal to negative 2x dx. So we've got the x dx, but we don't have the minus 2, so let's move that over to the side. Negative 1/2 du is equal to x dx. And that u substitution transforms my integral into the integral from x equals 1 to x equals infinity of what is now negative 1/2 e to the u du. So let's find the antiderivative, which for the exponential function is just the exponential function, which we are now integrating from x equals 1 to x equals infinity. But since the limits are in terms of x, we need to make sure that our antiderivative is returned to being in terms of x. So let's put u equals negative x squared back into position. Alright, now to think about this limit, there are a few different ways to think about it. I think it might be helpful to go ahead and put that e back in the denominator. Because in my opinion, it's now easier to see that as x goes to infinity and x squared gets really large, e to the x squared gets really large, which means that -1 over 2 e to the x squared starts to get really, really, really small. In other words, if I quote-unquote plug in x equals infinity, the result of that is going to be 0. If I then subtract what I get when I plug in x equals 1, then that is also going to be a finite number. So because the number was finite, this improper integral converged, which means that the associated series, the one that I was given at the start of the problem, must also converge as a result of integral test. Now that we've had a chance to do a logically valid application of the integral test, let's have a look at some other applications of the integral test to see if those are logically valid or not. For example here, a student is considering the series where they're adding from 1 to infinity the terms of the sequence cosine pi k. Now the student looks at this function, cosine pi k, which is giving them the terms in the sequence, and they recognize that this function is something that can be integrated. If you integrate cosine of pi k, changing the variable from k to x, then the result of that will be equal to sine pi k over pi, as a result of something like chain rule. So the student goes ahead, they integrate the function that gives them the terms in the sequence, they get sine pi x over pi, and then they evaluate that antiderivative from 1 to infinity to see if that integral converges or not. But, of course, if you take the limit of sine as x goes to infinity, that function just keeps oscillating between +1 and -1. So they conclude that, hey, this integral doesn't converge, which means that this series must diverge as well. What do you think? There's a lot of information there, but is this application of integral test valid or not? This application is invalid. The student missed some work at the beginning of this solution process. The student who is doing this argument never checked if the function that gave us the terms in the sequence was continuous, positive, decreasing. In fact, cosine of pi k is going to run into problems with both of these last two requirements. Cosine pi k becomes negative, dips below the x-axis on a regular basis, and it also is increasing sometimes. So these last two conditions are not satisfied. Which means that the integral test is still locked. Which means that it was never appropriate to use the integral test in the first place. How would we actually show that the given series diverges? I think this is a prime opportunity to use the divergence test. If I look at the limit of the original sequence, if I just look at the limit of cosine pi k, then that limit does not exist. The series diverges as a result of divergence test. It's completely unnecessary to go through this process of using integral test, and in fact, using integral tests at all is inappropriate for this problem because the hypotheses aren't fully satisfied. Let's have a look at this second use, and let's see if this is logically valid or logically invalid. Okay, so the student considers the series where we're summing as k goes from 1 to infinity, natural log of k divided by k. They notice that this formula for the terms in the sequence once again can be integrated. If you integrate that function with the u substitution u equals natural log of x, then the answer will work out to be natural log squared of x divided by x, which can then be evaluated from 1 to infinity. However, if you try and take this antiderivative and evaluate it at infinity, that limit doesn't actually exist. So the series diverges. So what do we think? Is this a logically valid argument or not? I'm going to go ahead and call this kind of logically valid. I would go ahead and call this acceptably logically valid. However, there is a technicality that has not been addressed by the student. And the technicality is the same one that created problems in the previous work. The technicality is, have you ever confirmed that natural log of x over x is continuous, decreasing, and positive? So if you wanted this to be perfect, if you wanted this to be completely airtight, here's the technicality that's missing. So here I am once again on Desmos, looking at the graph of the function in this problem, natural log of x over x. Now, as we can see, the graph of this function is not always positive, and it's not always decreasing. But it looks like it starts to become positive and decreasing. Guaranteed, it looks like it's happening to the right of the number e, 2.718. But just to be safe, I'm going to go ahead and say that the function in this problem is continuous, positive, and decreasing to the right of the number x equals 3. So technically, what we can safely conclude is that the sum, as k goes from 3 to infinity, natural log of k over k, does converge. But remember that convergence of a series does not depend on the series' starting position. Starting position affects the series value, but it does not affect whether or not the series has a value. So if you know that the series starting at 3 converges, it must be true that the series starting at 1 converges. So this would be the addition that I would make to this argument to make it absolutely airtight, flawless, and perfect. I would acknowledge the fact that the formula that I have is only continuous, positive, and decreasing starting from x equals 3, which means that the series converges starting from k equals 3. But because convergence is not affected by starting position, that implies that the series converges starting from k equals 1, corresponding to the series that we were given at the beginning of the problem. At this point, I want to get started on a very useful but lengthy exercise. What I'm going to try and do in this exercise is I'm going to try and determine convergence/divergence of a whole bunch of different series in one argument. I'm going to try and determine convergence/divergence for every series of the form 1 over k to some power. So in this one shot, I want to be able to consider series that look like 1 over k to the power minus 2, 1 over k to the power 1/2, 1 over k squared, and 1 over k. I'm going to try and do a single argument using the integral test and the divergence test to analyze all these possible different series at one time. And I'm going to break it down into 4 main cases. The first case is when this power p is less than or equal to 0. For example, such a series would be something like 1 over k to the minus 2, where the power is minus 2. Then I'm going to consider the case where the power is squeezed between 0 and 1. I'm going to consider a special singular case where the power is 1 exactly, and I get the series 1 over k. And finally, I'm going to consider the case where the power is anything larger than 1. For example, the case where we have the sequence 1 over k squared for our series. Alright, so let's get started. Case 1, what if the power is less than or equal to 0? If the power is less than or equal to 0, let's think about what would be true if I took the limit as k goes to infinity of each of the terms in the sequence. And it may help to consider the associated example where we have the sum of 1 over k to the minus 2. If the power p is less than or equal to 0, then the power negative p must be greater than or equal to 0. Which means that I am taking the quantity k and raising it to a positive power. As k gets larger and larger and larger, k to a positive power is going to get larger and larger and larger. Which means that this limit definitely does not converge to 0. Technically, it is either equal to positive infinity if this power is something that is strictly positive, something like p equals 2. If I take k squared and let k go to infinity, the entire quantity k squared will grow to infinity. And if the power happens to be 0 on the nose, so that I have k to the power 0, which is equal to 1, then that limit is going to be stable at 1. Now in either case, the limit is not converging to 0. It's either diverging to infinity or it's converging to 1, which is not equal to 0. Which means that in either case, the div test is unlocked, and we can conclude that the series must diverge. So case 1, where the power of this series was less than or equal to 0, we have concluded that the series must diverge in this case. So I'll put a D for diverge here. So let's then consider case number 2, where 0 is less than, the power is less than 1. So in this case, notice that the function 1 over k to the power p is continuous, positive, decreasing on the interval from 1 to infinity. You can confirm this using a particular example and using Desmos. For example, if you graph the function 1 over the square root of x, 1 over x to the power 1/2, then you can see that the graph is in fact continuous, positive, and decreasing. So it satisfies those conditions for the integral test. So let's go ahead and take the integral. So let's rewrite the integrand in the form x to the minus p. And let's go ahead and use the power rule to integrate this. So note that the power rule can be used here because we are assuming that p is strictly less than 1, so we don't end up dividing by 0 here in the denominator. Now let's think about what is happening to this quantity as x goes to infinity. And it may help to think about what is the nature of this power minus p plus 1. We get to assume that the power p is squeezed between 0 and 1. So that means that negative p, the opposite, has to be squeezed between the opposites, negative 1 and 0. Now if I go ahead and if I add 1 to everything, so that I have negative p plus 1, negative p plus 1 must also be squeezed between minus 1 plus 1, which is 0, and 0 plus 1, which is 1. So in particular, what I want to note is that negative p plus 1 is a positive number. So what consequence does that have if this power is positive, and I'm raising x to a positive power? Then x to this positive power is going to go to infinity as the base x goes toward infinity. So as a result of that, whenever the power p is squeezed between 0 and 1, the integral, the improper integral, diverges. And as a result of integral test, that means that the series must also converge. From an integral test argument, we have concluded that in case number 2, if the power that we're considering is not negative but between 0 and 1, then the series must diverge in this case also. For a different reason, the argument was different, but the conclusion was the same. Let's consider case number 3, where the power is exactly 1. And let's consider the series where we are summing up 1 over k, which is equal to 1 over k to the first power. This series is called the harmonic series. So let's consider whether or not the harmonic series 1 over variable converges or diverges. Now once again, the requirements of the integral test are satisfied on the interval from 1 to infinity. And you can confirm this, for example, using a graph. So let's integrate from 1 to infinity 1 over x, and when we do this, we get the natural log of the absolute value of x. Of course, as x goes to infinity, the natural log of x also goes to infinity, which means that the harmonic series has to diverge because the associated integral diverged. So finally, let's investigate case number 4. I had a typo originally, but this is the case where the power p is strictly larger than 1. As an example, we would have something like 1 over k squared, which is equal to k to the minus 2. Now in this case as well, if I look at the formula for the terms in the sequence, we still have the conditions of integral test satisfied. The function is continuous, positive, and decreasing on 1 to infinity, and as before, we can confirm that using a graph. And as before, if you want to find the antiderivative of this quantity, then just as in case number 2, you can use the power rule. But here is what's different compared to case number 2. In this case, our power is greater than 1, which means that the opposite of our power must be less than minus 1. So if I add 1 to that power, then the result must be a negative number. Because we're taking x and we're raising it to a negative power, this quantity is getting closer and closer to 0 as x approaches positive infinity. So as a result of that, finally we have obtained a case where the integral converges, and therefore the series must converge by the integral test. So to sum up the results of the previous theorem, we have a specific name actually for the collection of results that we worked so hard to get on the previous page. The series of the form 1 over k to some power, any series of that form, is called a p-series. And so what we have just done is we have determined exactly when a p-series is convergent. We found that if we were in either case 1 or 2 or 3, if our power was anything less than or equal to 1, then the series had to diverge. It was only in case number 4, where our power was strictly larger than 1, that our series finally ended up converging. So, having invested all of this work into the p-series test, let's go ahead and have some fun using it to quickly determine convergence/divergence of a few following series. For example here, does the following series converge or diverge? And let's give a formal argument. We have the series where the formula is given by 1 over the square root of k. So in other words, 1 over k to the power 1/2. So the series that we have is a p-series. It's in the form 1 over k to a power, where the power is 1/2. But since that power is less than or equal to 1, then we know right away that the series must diverge by the p-series test. And that's it. The argument is done. We put all that work into getting the p-series test, but now that we have it, we can use it really, really easily and quickly in our arguments.
All of this just works.
Let's do another quick example. Does the following series converge or diverge? Give a formal argument. And we have the series 1 over k to the power 4. In this case, we have a p-series with p equals 4, and that number is strictly greater than 1. So the series must converge by the p-series test. In spirit, the p-series test is really similar to the theorem that we had for geometric series. If we had a series of a very specific form, geometric, then we had a really easy way to tell if the series converged or diverged. Once again here, if we have a series of a very specific format, specifically a p-series, then we once again can very easily and quickly determine whether or not the series converges. So as mentioned at the beginning of today's video, we're going through and we are developing a bunch of different techniques and tools to decide whether a series has a value, whether a series converges or not. But we still have very few tools to determine what the series' actual value is. And in general, it's an extremely hard problem to determine what a series value actually is exactly. However, in practice, what we can do is we can get an estimate for a series' actual value. And that's what the following theorem is all about. So suppose we have a sequence, a sub k, and we have a formula for that sequence. Let's call it the function f. And let's again suppose that this function is continuous, decreasing, and positive from some number n up to infinity. Now also suppose that in this context, you already know some way, somehow, that the associated series converges. Maybe you applied integral test, maybe you applied geometric series test, maybe you applied some other test, but you already have the information that the series does have a value. And now your quest is to try and get an idea of what that value, what that limit actually is. So here is your idea. Your idea is not to try and add up all the numbers in the series. Your idea is just to try and add up the first n numbers in the series. If you only add up n numbers in the series, how close are you, roughly speaking, to the series' actual value? The difference between the real limit and the one that you estimated, in other words, the error in your estimate, is squeezed between two numbers. The error can never be worse than the number that you get by integrating the function from n to infinity. But the error that you get will always be worse than the number that is equal to the integral from n plus 1 to infinity. In other words, the error is never worse than the integral from n forward, and the error is always worse than the value of the integral from n plus 1 forward. Now let's see what it looks like to actually apply this theorem to a particular scenario. This is quite a famous problem in mathematics. It took a long time to actually get the answer to this problem. And the problem was, what is the actual value of the number that you get by adding together the reciprocals of squares? 1 over 1 squared, 1 over 2 squared, 1 over 3 squared, and so on. We know from the p-series test that this must converge to some number. But the problem that was outstanding for a long time is, what number is this actually? Now, this was finally figured out a few hundred years ago. If you recall from video number 4, the value of this sum is equal to pi squared over 6. But this was an extremely difficult result to actually get, to know that this number was exactly equal to pi squared over 6. So let's see if we can estimate the value of this series using these error estimates from the previous page. So suppose that we estimate the value of the series using the 10th partial sum. So instead of adding up all the terms in the series, we only added together the first 10. Worst case scenario, how far is our estimate from the series' actual value? Okay, so we estimated the value of the series using the 10th partial sum, which means that we estimated using the partial sum corresponding to n equals 10. So scrolling back up to the previous theorem, the error that we incur estimating with the nth partial sum, in our case the 10th partial sum, worst case scenario is given by the integral from n to infinity of the function corresponding to our sequence. So let's go ahead and let's calculate this value. If I integrate this using the power rule, I get x to the power -1, evaluated from 10 to infinity. X to the -1 goes to 0 when x is infinite, so I get 0 minus -10 to the -1. After some simplification, this is equal to 1 over 10, or if you prefer decimals, this is equal to 0.1. So to rephrase what we have obtained here, if I estimate the value of the series using the 10th partial sum, that number is going to be within 0.1 units of the actual value of the series. Now, off to the side, over in my spare time on Wolfram Alpha, I've gone ahead and I've calculated the value of the 10th partial sum, and that works out to be about 1.54977. That is the value to 5 decimal places. Whereas the real value that was calculated through some very, very hard work, the real value of the series pi squared over 6 was equal to 1.64493. So the actual error in this case, you can check the difference between these two numbers is 0.09516. The error between the value of the 10th partial sum and the real value of the series pi squared over 6 is indeed smaller than 0.1. But more useful perhaps is the application in the following scenario. Someone says, okay, for whatever application, for whatever purpose we're doing, we need to guarantee that our estimate is within 0.0001 units of the right answer. Maybe somebody is building a bridge or launching a rocket, and if the error is anything in excess of this value, then the bridge is going to collapse, the rocket is going to miss its mark, and billions of dollars will be wasted. So we want to make sure that worst case scenario the error is still smaller than this 0.0001. Now the worst case error is given by the integral from capital N to infinity, the function representing our sequence. So let's see if we can simplify and evaluate the integral on the left side, and let's see if we can get an estimate for the value of n, which makes this inequality true. So once again, we're going to come in and we're going to use power rule to find the antiderivative. If we evaluate that, we get n to the -1, and we want that to be smaller than 0.001. So if we rearrange this a little bit, it may help to think of this as 1 over n. If we rearrange this a little bit and swap the positions of n and 0.0001, This implies that n must be greater than or equal to, or I should say, n must be greater than 1 over 0.0001, which means that we need n to be greater than 10,000 units. As long as we calculate a partial sum with more than 10,000 terms in the partial sum, we will in fact have an accurate representation of the true value of the series to within an acceptable margin of error, 0.0001. So for example, we could use 10,001. Once again, over off to the side, I've gone ahead and calculated the actual values of the partial sum up to the 10,001st term, and I have gotten a decimal approximation for pi squared over 6, which is the true value of this particular series. And you can see we have just sort of barely made it. The S sub 10,001 is different only in the 1, 2, 3, 4, 10,000 position compared to the actual value. So we have just barely satisfied the requirement for the error. To summarize what we did today, we introduced the integral test and we practiced using it. We looked at some invalid applications of integral test. Then we used the integral test to get another theorem that we could use to quickly determine convergence or divergence of so-called p-series. Finally, we used integrals to get an estimate for the worst-case scenario for the error that we incur when we estimate a series using the nth partial sum.